taking on those. And there's also an older edition in the library. And if worse comes to worse, I can make some copies of those chapters. So anyway, the whole book is talking about dynamical systems in sort of biology. This one also is, there's an older version in the book in the library. I don't know if it's the latest version, but it looks really beat up. Anyway, so I can make copies of the respective chapter if you, okay? But the most important thing is I put a timeline here, so I want by the 9th of March for you to decide on a project and let me know. By April 6th, so that's after spring break, I want an initial report. And again, I think for each project I kind of have an outcome that I kind of expect, but this can be flexible. So pretty much in the initial report I want people to describe the project. How are you gonna? What kind of questions are you asking? How do you think how do you plan to ask it? What's your outcome gonna be like? Pretty much a month later, May 4th, I want everybody to be almost done. I mean, maybe not dot all the I's and cross the T's, but I'm planning some sort of 15-minute presentation in class that week, May the 4th. And I put here the last day of classes as the final report, the paper being submitted. Okay. I think our final exam is a week later, so it's the 18th. So we'll see how that is going to play out. But okay, so this is mandatory for grad students, but undergrads are more than welcome to look at these. And the starting point for each chapter, for each project, is that chapter in the book. At the end of each chapter, there is some sort of, at the end of each chapter in the book, there is a section that talks about some kind of further explorations. So that would be a good starting point. Okay, so I'd say, even though we haven't covered a lot of the tools that you'll need, since most of these are nonlinear systems, we're still talking about linear systems. So we haven't covered most of the tools, but I think you should get an idea by looking at those chapters, and also your interests. I think somebody already contacted me with a preference on a project, so that's good. Yep.
How are you choosing which project you're doing? Is it whatever you say you want to do, you get to do that, or are you going to try?
You pick. If your major is in philosophy, you probably have a hard time picking. But I don't know. Some are majoring in mechanical engineering, so that seems to be. And again, I want to be. I mean, these are topics that I found sort of. I mean, they're extensions of what we talk about in the book and so forth. So the fact that I put here motion and central force fields, it's not necessarily. I mean that. The only thing of interest in classical mechanics, but it's kind of a manageable topic, I think. So we can be all flexible about this, but I don't know. If you're electrical engineering, you might want to choose this one. If you're math major, you can pick any of the three. See, that's the advantage. Woohoo!
And you still thinking it's 2 students per project? Or?
Doesn't necessarily have to be. When it comes to presentations, it would be okay to. I mean, it would be either way is fine. But I'm thinking if there are 2 students working on a topic that each chooses to present one model. Because as you'll see in this outcomes, I'm asking to kind of pick several models that describe phenomena in each of the topic areas. So, sorry, the presentations that the project can be in the same general area, but with different, slightly different focus.
But each student will have an individual report.
Yes, definitely. So, okay. Any other questions? Do undergraduates get extra credit for working on this? Of course. The whole point here is that you kind of get exposed to other more sort of applications of this ordinary differential equations. Okay. So start thinking about this, and I can see what I can do about maybe distributing copies of this. Let's see, another thing that I wanted to mention was I posted the next homework. It has a few problems from chapter 5 that I took off last time, and a few from chapter 6. So and I put the due date of Friday. Is Friday going to working, or because as I said last Friday I only got very few.
How about the next Monday?
Leave it for Monday? Okay. Monday's fine too, I don't care. So I can put it for Monday. Okay. Okay, so one main thing that we just touched upon last time was this canonical forms for matrices that are bigger than just 2 by 2, okay, 3 by 3 or higher. And this is a topic that it's covered extensively in other courses. I'm not sure how much was in the introductory course to linear algebra that you had. I put a link here to some notes that I have, but I put it as an optional because really it's whoa, okay, and of course it's broke. I didn't upload the file, so I'll upload the file, and you can take a look, and I'll talk a little bit about it today in class. But unfortunately, we're not going to have time to just go over the whole theory. Okay, so I wanted to just get the results of this theory and how you can decide on which canonical form your matrix can be brought into. Okay, so each matrix has can be transformed through a change of variables or of coordinates into canonical form, right? So let's say that. So if A is an n by n matrix, then A has n eigenvalues, complex eigenvalues, right? And possibly repeated. So when we talk about n eigenvalues, they could be repeated, right? So an example is let's say the characteristic polynomial is what gives you the eigenvalues, right? It's setting the determinant of a minus lambda identity equal to 0, right? So the characteristic polynomial is a polynomial of degree n, so it has n complex roots, right? Lambda 1. Now, if I am to count them with, so I could list them as sort of with their multiplicity. So if there's a repeated eigenvalue of multiplicity 2, then I list it twice, right? But you can also say there are lambda 1 through lambda k distinct eigenvalues, right? And each comes with a multiplicity, m usually it's called. There are some powers, right? So MIs are called or MJs are called the algebraic multiplicities. So, like the example last time was, I don't remember what the matrix was, but we ended up with a polynomial, or with the equation lambda minus I square lambda plus I square equals 0, right? So it means I have lambda 1 equals I and lambda 2 equals negative I, each with multiplicity 2, right? So, by writing that determinant of lambda minus a minus lambda identity and factoring it, well, in theory at least, you can see how many distinct eigenvalues are and with what multiplicity they come, right? Now, if there is a complex eigenvalue, then there is also its complex conjugate, right? And the multiplicities of those are the same always. Why? Well, they come in pairs, but also it has, like, if this is square, this cannot be cubed. Why? Because the ones that are same powers, then they be combined into a quadratic polynomial with real coefficients. Okay. Of course, I'm talking about matrices that have real entries, right? So since the matrix has real entries, then you cannot have isolated, like, an extra factor of lambda plus I, right? Because the characteristic polynomial is real, has real coefficients, right? So this has real coefficients here. Since we're talking about with real entries, we will not talk about differential equations or the system of differential equations with non-real coefficients. Okay. So, focus is still on systems, but again, talking a little bit about the matrix coefficient. Okay, so that's a little bit of the structure of that. And for each eigenvalue, so there's a lot more in that handout that I posted there, but for each eigenvalue, lambda j, for instance, okay, let me define the following thing. E lambda j, which is the kernel, I'll say in a second what it is, A minus lambda j identity, is called a kernel or null space of A minus lambda j I. And it could be denoted by and too. I don't know which notation you've used. But what this is basically the collection of vectors for which this matrix multiplied by that vector is 0. So what do you recognize this to be? The eigenvectors corresponding to that eigenvalue, right? So for each eigenvalue, there's this set of vectors, right, in Rn, so n-dimensional vectors, for which this is happening. And notice that we also include 0. So 0 is also part of this. It's called an eigenspace. Okay, so this is called the eigenspace, corresponding to that eigenvalue. So it is called the eigenspace of A corresponding to lambda J. Okay. So the big thing here is how big is this eigenspace? Okay, for each eigenvalue, how big is this eigenspace? We said that it's possible that you have more or fewer or more eigenvectors that are linearly independent from each other in each eigenspace here. Okay, so the key is so the most important thing in canonical forms is determining the dimension of E lambda J. Okay, and what do we mean by dimension? We mean the number of maximum number of linearly independent eigenvectors for, in this eigenspace. Okay. Now, does everybody know what linearly independent means? No, yes, no. So within each eigenspace, you have to be able to find the number of, not necessarily find the basis, find the linearly independent eigenvectors, but just find the number of linearly independent eigenvectors. Okay. Well, how do we do that? Okay, so how does one find this maximum number of linearly independent eigenvectors? Well, there is what's so-called a dimension theorem, which says for an n by n matrix, the dimension, and it's called dimension, so DIM. So the dimension of this kernel plus the dimension of what's called a range is always n. So n is the dimension of the matrix. Okay, so you recognize here is the Eij, right? What is this range? What is the range of a matrix, for instance? Has anybody heard of the range of a matrix? You usually hear of range of a function, right?
Is it the number of linearly independent eigenvectors?
No, this is it. Maximum number of independent eigenvectors is this. But just these, like forget the dimension, just the range. Usually you have a range is for a function, right? Right? You have the function f of x equals x squared. You draw the graph and you say the range is positive, right? So for a matrix, come on, nobody heard of the range of a matrix? Okay, anybody heard of column space of a matrix? What is that? So that's what the range is in this case. Range of a matrix B is the column space of a matrix B. And what do we mean by that? Well, here's what we mean. we basically say that I take a vector in xn, in Rn, excuse me, in Rn. So I take a vector in Rn, and I build a map, like a function, between, like the same way as this one. This is a function from R to R, right? Well, here's going to be, the matrix is going to be a function that takes a vector in Rn to what? To guess what? To the matrix B times X. Okay? So the range of this matrix is really the range of this function, or linear transformation. I don't want to. This is called a linear transformation. Right? You take them. So the matrix B acts on each vector in Rn by multiplication with that vector, and it gives you another vector. That's a linear transformation from Rn to Rn. Okay? So now you can think of the range as being, what are the possible targets? What are the actual targets in this Rn? Well, it's possible to be the whole Rn, or it's possible to be just a subset or a subspace of that. So the range is always, well, it's certainly a subspace. So it's closed. If you add two vectors, then you stay in that subset and so forth. But okay, so we like to write this as sort of. I like to represent it like this. So it takes the collection of all vectors in Rn, but it kind of possibly shrink it, in dimension. Okay, so it's going to be a subspace of Rn, so we'll have a dimension less, possibly less. Okay, in fact, that theorem is actually saying how much less. So I'm talking about B as being this A minus lambda I. So what is that theorem saying again now? It says the dimension of the range, so the dimension of this target, or of this image, or of this column space, is n minus the number of linearly independent eigenvectors. So for a given eigenvalue. So, like, if lambda is an eigenvalue, we know that that kernel has at least one eigenvector, correct? So you see that range is always at most n minus 1. Okay? So if there's only one eigenvector, linearly independent eigenvector, then the range is n minus 1 dimensional. If there are two linearly independent eigenvectors, then the range is dimension n minus 2, and so forth. So it's like a complementary, right? Okay. Well, there is a proof, a short proof that you have in the book. So I just want to refer to that for the proof of this, since this really belongs to a linear algebra course, and this is usually covered in the even in the introductory course. The idea, though, has to do with how you build basis of that range, and you complete it to some sort of vectors from the null space or from the kernel, and then you count and you get that the numbers add up to the dimension of the space. Okay. So if you haven't looked at that, please look at that proof and let me know. We can go over. But what's more important is how to apply this, and why is. So our goal is to find the dimension of this eigenspace, right, for each eigenvalue. How to use this fact. So why is it easier to compute the range or the dimension of the range? Do you know? So what is the dimension of the range? So it turns out that it is easier to compute dimension of the range or of the column space. Okay? And this has a name. Anybody? What's the dimension of the column space of a matrix? What's a column space? Column space is the subspace generated by the columns. Right? So for example, I think one of your homework was, well, 3 by 3. I mean, it's certainly this is work for any dimension, but let's just take this for simple simplicity. Take this matrix, and if you compute the eigen values, you end up with what is it, lambda square, lambda minus 1, something like that. So so it means that lambda 1 is 0 and lambda with multiplicity 2 and lambda 2 is 1 with multiplicity 1. Yep? Okay. I hope that's correct. Anyway, so what's the let's start with lambda equals lambda 1. A minus 0 times identity, of course, is just A. So it's this matrix, right? What's the column space or the range of this matrix? Well, if you take the column space is, as I said, is all linear combinations of the columns. Well, all three columns are the same, so all the linear combinations will be it will be one dimensional, right? So the range of A is, what do we say, span of, that just means linear combinations of this, because there's only one column, right? So how many linear independent eigenvectors are there? 1, right? Well, again, what is the dimension of the range in this context called? It's called? Have you heard of rank? Rank of a matrix. Rank, okay? Rank is the maximum number of linear independent columns of a matrix. That's exactly the dimension of the range. Okay? Why is the columns? Why do I keep saying that the range with that picture that I had is images of A sub A times X is identical with the column space? For any matrix, the range of B is the same as column space. So the range of B is defined by all images through B of vectors in Rn, right? Column space of B, I said, is the linear combination of the columns of the matrix. Why are they the same? Right. So what the columns are images of which vectors through this B? Well, take the vector 1, 0, 0, 0. The book likes to use capital E's. Can I use little e's? Okay, I use capital E for the eigenspaces. Okay, so take E1 to be this vector in Rn, right? If you apply the matrix B, multiply with E1 with that, then it's just the first column survives, right? So that means the first column is actually an image in that picture of this vector, right? In fact, each column is going to correspond to one of these vectors in the standard basis. So E2 is going to be 0, 1, 0, 0. B2 is C2, and so forth, right? So you can see that basically the set of columns, so its span is in the range, right? But you also need to show up the other way around, right? So again, this implies that the column space of B is included in the range of B, but the opposite is also true. So in the end, these are the same thing. So how can you argue that something in the range of B is a linear combination of the columns of B? Well, let's just take Y in the range of B. What does that mean? It means that Y is B times some X for some vector X, right? So what does that mean? That means you have a system of equations. So it means B times x1 xn equals Y. And when you think about this, B times x1 xn, well, what is x1 xn? This vector is a linear combination of the E1 en, right? And I'm going to put a vector here just so. x2 e2 plus xn en equals Y. And now because it's linear, you can have x1 be e1 plus x2 plus xn be en. And we just said C1 is BE1, xn is Cn is Ben. So you see Y is in the span of C1, Cn. So that's the column space, right? So this means that the range of B is included in the column space of B, right? So it means that the range of B is actually identical with the column space. Okay, we just proved that. I mean, I don't know. If you've never seen this before, it's probably kind of a weird thing. But it's just to tell you that when we look for the dimension of the range, it's the same as looking at the dimension of the column space, which is called the rank of the matrix. So how do we compute the rank of a matrix? Well, of course, the easiest is to figure out which columns are linear combination of the others, right? So, of course, if they're all three the same, obviously only one is a linear independent, so the rank is 1. But how about, let's take the other one. So back to the matrix A. But now let's take lambda as lambda 2, which was 1. Can be 1. Is it 1? Is it 1?
Yeah.
Are you sure? That's what I wrote, but I'm not sure now. This was in the homework, so let me... No, it's 3, excuse me. It's 3. Yeah, something doesn't sound right, so lambda squared minus 3, so this is, lambda 2 is 3, okay? So, it means the matrix A minus 3 identity is negative 2, 1, 1, 1, negative 2, 1, 1, 1, negative 2. And what is the rank of this? Well, it's the maximum number of independent columns, right? How do we compute the rank of a matrix? We go to MATLAB and ask, give me the rank. Okay. But in the exam, you want to have MATLAB? Yeah.
Well, couldn't you, it's probably the most efficient way to put it in RREF and find the number of pivots?
Yeah, that's one way, certainly. So Gaussian elimination, reduced row echelon form would tell you the rank by looking at the number of non-zero pivots. Okay. Well, let's say that's so long ago and rusty you don't even want to do RREF. What's another way? Well, not that it's necessarily always quicker, but you look at the, for example, if it's, can it be rank 3? Can you have rank 3?
No.
No, why not?
Because one within the other, I get what you said.
Because the determinant of this, that's how we found 3. The determinant of this is 0. That's a matrix that is determinant of 0 means it's not invertible, right? That means the columns are not linearly independent. So you cannot have 3 linearly independent columns, right? You see, the rank tells you how big that image, that range is, okay? To have a matrix of full rank, like rank 3, that's the maximum it can be, right? For this matrix to be rank 3, it means that the image is the whole R3, right? It means that you would be able to do it to be invertible. It would be, you would be able to find that inverse. But we know that's how we found this 3, so we don't have to check that the rank is 3, okay? But we have to check whether the rank is 2 or 1, okay? How do we check or that the rank is 2? We have to be able to find 2 linearly independent columns. 2 linearly independent columns, okay? And the easiest way to do that is, well, okay. For 2, it's easy because, you know, how can 2 columns be linearly independent? One is not to be a multiple of the other. So that's easy, right? You can see the first and the second are not linearly independent of each other. But, so, the answer is rank is 2, right? But, in my opinion, the best way is to find a 2 by 2 matrix, submatrix, or called minor, whose determinant is not 0. So if you go and search and say, here's a 2 by 2 determinant that's not 0, then the columns, or the rows, but the columns on which that determinant sits are going to be linearly independent. Okay? So that's the best way. So the rank of a matrix in summary is what? Is the biggest, the size of the biggest determinant that's not 0 in a matrix. I mean, minor, it's a subdeterminant, yeah.
So if it was 4 by 4, you'd have to find a 3 by 3?
Well, you would look for a 3 by 3, but you may not find. The rank might be 2, or it might be 1. Okay. So it's but that's how you kind of go down and size, and you say, can it be rank 2? I mean, it's not the most efficient, but if you see one determinant which is not 0, and it's like, it's in a 7 by 7 matrix, and you just spot one that's 3 by 3, you know the rank is at least 3. If you see a determinant, like a sub-matrix, whose determinant is not 0, that's size 5, okay, and then you, I mean, again, RREF is always going to work for no matter what, but you may have to compute a lot, Gaussian elimination. So, but you know, for 5 by 5 and 6 by 6 you may have to use a computer anyway. So we're just talking about things that you can see really kind of quick. Okay. So in this case, rank is 2. So what does it mean about the dimension of the kernel? It's 3. It's 3 minus 2, right? So that's n minus the dimension of the range of the rank. So it's 1. So what does this mean? Only one eigenvector, linearly independent eigenvector for this eigenvalue. Yeah? Going up here, when we talked about lambda equals lambda 1, which was 0, and we found the rank of that to be 1, what did they say about dimension of the kernel of A minus 0 times identity? 3, that's n, minus 1, so that's 2. So this means there are 2 linearly independent eigenvectors. Okay? How do you find them if you have to find them? Well, just write the system and RREF, basically. Okay? But in a lot of these cases, we don't have to find, we don't have to do that extra linear algebra computation of finding the eigenvectors. We just want to know the number of linearly independent eigenvectors, the number, multiplicity of eigenvalues, because we are interested in the canonical form. Okay? So, what is this? So I said that's the key. Finding the number of linearly independent eigenvectors is the key to figuring out what the canonical form and it's called Jordan canonical form should be. So we said this last time. If I have an eigenvalue that has, well, we have, it's a 3 by 3 matrix with only 2 eigenvalues. One is repeated. And for the repeated eigenvalue, we have 2 eigenvectors. What's the conclusion? The matrix is, the canonical form is the diagonal. Why? And on the diagonal you put the eigenvalues, right? This was 3, I'm sorry, I keep putting 1 here. So it's what we call diagonalizable. It's diagonalizable, so it has this expression. Let's call it J, and of course T inverse AT. There is a T, right? That's a 3 by 3 matrix, such that T inverse AT is that Jordan form, is that in this case diagonal form. Okay? What if I have a 3 by 3 matrix with 2 eigenvalues, 1 repeated, and only 1 eigenvector corresponding to that repeated eigenvalue? I think there was another example in your homework. There will be only one block called the canonical Jordan block with a 1 on top, and of course this other one would be the same. Let me see if I have an example here really quick. Yeah, so this was the other one. I'm just kind of, since you've done the computation, hopefully. 0 1 0 1 0 0 1 1 1. Okay, turns out lambda 1 is 1 with multiplicity 2, and lambda 2 is negative 1 with multiplicity 1. Okay. Then we end up with for lambda equals lambda 1 equals 1, what's A minus identity? So that's the B matrix, A minus identity. Minus 1, 1, 0, 1, negative 1, 0, 1, 1, 0. Okay? What's the rank? What's the rank? Why is it 2? There, you can find two columns that are linearly independent of each other, right? So the first and the second. Or, my favorite, I can find a 2 by 2 determinant, minor, even this one, right? No, this is no good. This one here. That is 1 minus minus 1 plus 1. Determinant 2, non-zero, so these two columns are linearly independent. Okay? So what does it say about the number of the linearly independent eigenvectors? Well, it's a complement of 3. I mean, it's what it takes to add up to 3. So it's 1, so it means that only one eigenvector. Okay? Now, being only one eigenvector means that when you try to diagonalize that, you don't have enough eigenvectors. Well, let me make this comment too. For the other one, which is a simple, I don't even have to compute this. I know the rank is going to be 2. And we can talk about why this is, but the bottom line is if the eigenvalue is simple, there's going to be only one eigenvector. You see, let me call this x3 here. This is x1. Okay, I leave x2 for what's needed there. But when I have a simple eigenvalue, why is that? Why do we know that there's only one eigenvector, and not? Why couldn't there be two linearly independent eigenvectors corresponding to that eigenvalue, which is simple? Because the eigenvalue has multiplicity 1. So you see, I mean, there is some linear algebra that's involved there, but when you have, let's say, lambda 2 here, you know, if you had two eigenvectors, then you could put them, you know, x, here I'm sort of out of, I mean, I have to change some notation here. If I think about a big matrix, okay, a big matrix, and I have the eigenvalue lambda to be simple, this means I cannot have two eigenvectors corresponding to this eigenvalue. Because if I did, I could find sort of a change of coordinates for which these are part of those matrix T, and then I would get two lambda 2s here. And of course 0, 0. And then I don't care anything else there. But this, if you do that determinant, you would not get it to be simple eigenvalue, right? So this would not be a simple eigenvalue. Simple with M2 equals 1, right? So it would not be equal to 1. It would be at least. You see, the multiplicity of the eigenvalue that appears in that characteristic polynomial is at least the dimension of this eigenspace. And again, all of the statements have proofs in a linear algebra course. I'm just kind of giving you the essential information that is will help us get through this. So we don't have to really. I mean, of course you can convince yourself in this case. Rank of that matrix is 2. So there's only one eigenvalue. So what do we do? As I said, because we have only one eigenvector corresponding to a eigenvalue that has multiplicity 2, then we have to construct that generalized eigenvector. Okay? So since lambda 1 has multiplicity 2, but only dimension of the kernel, but only dimension of this eigenspace equals 1, then we need to find x2 such that a minus lambda x2 is x1, called generalized eigenvector. Now, who tells us that we can do this? That was the question in one of the homework, which was pretty tough actually, thinking in hindsight. But unless you have this image of the map, of the function, of the range, it's hard. Because think about it for a second. If I have that's the B, right? That's the B, which is A minus lambda identity. Okay, so that's that map. Okay, and now I'm saying, well, what's the kernel of this map first? Well, the kernel is simply the set of eigenvectors, so is the eigenspace. Okay? So what's the range? Well, whatever the range is, the statement here says for that one eigenvector, in this case is just one eigenvector, how do I know that I can solve this linear system? How do I know that x1 is actually in the range of this matrix? That's what it's saying. So the fact that we can solve this says, or we need to check that eigenvector is in the range of this guy. Okay? Alright, so, and that's not obvious at all. Alright? It's not obvious at all. In fact, why is it not obvious at all? You see, let's just focus on this particular example. So let's talk about dimensions. This is R3, this is R3, yep. And we said the range, so the rank of this is 1. Okay, so it's one dimensional. So it means it's a span by one vector. Okay, so it means it lives out two dimensions, right? The kernel, no, the kernel of this is one dimensional. There's only one eigenvector, okay? The kernel of this is one dimensional. So the range is two dimensional, okay? So I put this as 2, but I'm just counting dimensions, okay? So I'm saying there are two linearly independent. How do we know that x1 is not here? And it's here. See, that's the whole. And that's why it takes all that construction, that is explicit in the handout. But how do we know that the eigenvector is actually in the range? Okay, so that we can find x2. And the answer is imagine it would not be in the range. Imagine it would be here, right? Can you imagine for a second? Proof by contradiction. Imagine x1 would be here, outside of the range. So this had no solution. Are we all on the same page? How do we get a contradiction? Well, the contradiction is the following. Well, this is all R3. The contradiction is the following: is to take this range and apply B again. Okay, so B takes the R3 into a two-dimensional, right? And now apply B again. Okay, now what happens is, and you can think about it in your free time, why something that's in the range is sent in the range again. Well, something in the whole space is sent in the range. So of course something in here is also going to be sent here. In fact, it's going to be sent into something smaller, right? That's one-dimensional. Okay? But just think about B sort of as a so think about the restriction sort of a B into that subspace. Okay? If you think about the B as a restriction in the subspace, then what you can see is that restriction has eigenvalues of its own. Okay? Has eigenvalues of its own. And what are the possible eigenvalues of this restriction? Well, they have to be eigenvalues for the full matrix as well. Okay? So they can be 1 or negative 1. The fact that you left out, the assumption was that x1 was outside of this range, says that 1 is not an eigenvalue for this restriction, right? So then you have a 2 by 2 matrix that has just one eigenvalue. Well, that has to be repeated, but negative 1 was not repeated up there. Okay? So that's sort of how you make the argument. This is a little bit more complicated than what that problem 9 in your homework was asking, really. Okay? But it's the same construction. So I said a lot of words. I didn't write much. So assuming the contrary, that is, x1 is not in the range, would lead to a contradiction. Since lambda 1 must be an eigenvalue for this B restricted to the range of B. So that's that restriction over there, from red to green. Okay. So it must be an eigenvalue. So it must have an eigenvector. Okay. So there must be an eigenvector in that range. All of this, though, has a very important, I mean, it's really part of that grand theory of Jordan canonical forms. Anyway, to conclude in this particular case, if we have two, we said we have 1 and 1 as a repeated eigenvalue and -1, right? Well, since we only have one eigenvector, we have to create one block, and that corresponds to x1, x2, where x1 is eigenvector, x2 is generalized eigenvector, and x3, of course, is eigenvector. So T is this, and this is J, then T inverse A, T is J. Okay? But this is eigenvector for lambda 1 equals 1. This is eigenvector for lambda 2 equals -1. And this is generalized eigenvector for lambda 1 equals 1. Okay? And notice that we haven't really computed any of that, x1, x2, x3. Okay? So we do it only if we need to. Okay? But again, the key is to get the structure of these things. Yeah?
Do they need to be in that order?
Yeah, that's a great question. So they don't have to be in this order. We always know that the change of variables can be, I mean, the order in which you write the vectors here will certainly influence that thing here. But you don't, I mean, it's not unique. In other words, you can put x3, x1, x2. Then this block is going to be before this block. Okay? But you cannot swap x1 or x2. That has to be in this order, because x1 and x2 creates this block. If you were to swap x1 and x2, guess what would happen? The one would be on the bottom. Okay? So when we say Jordan canonical forms, okay, we set in stone that above the diagonal, we put the ones above diagonals. Okay? All right. Let me quickly say that if A is 4 by 4 and only one eigenvector, only one eigenvalue, lambda with multiplicity 4, of course, and only one eigenvector. So dimension of the eigenspace is 1. What's the canonical form? Well, the question was asking, prove that you can bring it in this form, lambda, 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 lambda. Just one block, right? So how many blocks are you going to get? The number of blocks is going to equal 1. In this case, 1. It's always going to equal the number of eigenvectors, independent eigenvectors. So for each eigenvector, there's going to be one block. Okay? That's why when you have n eigenvectors, independent eigenvectors, you're going to get n blocks. That means it's going to be diagonal, right? But the moment you have fewer eigenvectors, linear independent eigenvectors, for some eigenvalues, it's no longer going to be diagonal. There's going to be these blocks popping up, right? And we really didn't talk about the size of each block. We just talked about the number of blocks, right? So for the size of each block, there's a whole different theory. But in this case, it's basically says, well, it's one block, has to populate a 4 by 4 matrix, so it has to be a 4 by 4 block. Well, how do we get from this knowledge to this? So knowing there's only one eigenvector for the only one eigenvalue with multiplicity 4. How do we get this? Well, what you need to do is to argue why you can find an x2 to solve this equation, correct? And then so what does this mean? This means x1 is in the range of A minus lambda identity. Okay? So you have to tell me why. Why is that eigenvector? Why that eigenvector must be in the range? Then with x2 you have to do the same. Y means x2, which was found in the previous step, is in the range. And finally, x3 is also true. I mean, you have to show that x3 is also in the range. Once you've established this, well, then you can just put x1, x2, x3, x4 in that order, and get this. Put T inverse AT, and get that Jordan block. Okay. So can somebody tell me why? Let's start with this. Why is x1 has to be in the range? Let's draw a picture here. So this is a 4x4. So we said the dimension of that kernel is 1. So it means that the range of this is three-dimensional, right? So how do we know that x1, that only eigenvector is in this range and not outside of the range? Well, it's exactly that argument, right? So this is if this is it really helps to have the concept of linear transformations, and I'm not sure how much of that you've seen in linear algebra courses. But it's really saying, you take, so don't think of matrices as matrices, but think of them as linear transformations, as these actions from take a vector to A times or B times X. Because then it makes very, very quick sense as to what its restrictions are. So you see, it would be harder to think of what is the restriction of a matrix to a subspace. That's kind of tough to say, but the restriction of the linear transformation to the subspace is simply just restricted, just apply it to that subset. Okay, and that linear transformation in itself has eigenvalues and eigenvectors, right? Which have to be inherited from the bigger one, right? But the bigger one had only lambda; that was the only eigenvalue. So lambda has to be an eigenvalue also for this one. Well, what does it mean as an eigenvalue? It has to come with an eigenvector, right? Well, but there's only one eigenvector, so that eigenvector has to be in the range. Okay? So this means x1 must be in there. Well, because it's in here, it actually means that it comes from an x2. Yeah? Because that's what it says. It says B of x2 is x1. So that's how we found x2. How do we continue? Well, we have to show that x2 is in the range. So basically we move the picture by one more, and we do the same. We say again, it's the same argument, right? We keep restricting and we say, well, x1 is not just in the range of this, but it has to be in the range of this, repeated like iteration, b squared basically, right? So the x1 comes from an x2. Well, the x2 has to be in the range because we're talking about that restriction. So x2 comes from an x3. And then we move even one more, and we are able to go all the way to that chain of x4. So the x1 is here. So x2 is here. So x3 is here. And finally, okay, then finally you get x4. Okay? Anyway, that was so I didn't really expect. Yeah, I should have deleted that problem too from this homework. But anyway, you have another homework problem that I assigned, which says come up with all possible Jordan forms, canonical forms, when you have a 4x4 matrix, 2 eigenvalues, and I don't know, something about each the eigenvectors corresponding to each eigenvalue. Probably some deficiencies, so a number of eigenvectors less than the multiplicity. Okay. Now, let me just say one final word. Why do we care about the canonical form? Why do we care about canonical form? Well, because in the end we want to figure out, we want to see the picture, the solutions of the system x prime equals ax, and that's going to be coming next. Now that we know the canonical form and potentially the change of variables, the change of coordinates t, how do we look at the phase portrait? Now it's no longer plane in the plane because it's 3x3 or 4x4. So this ODE solve, which is a code, it's a miracle code, I think, because it lets you put. I showed you this. Of course, now it will cooperate. Come on. Okay, yeah, it has 3. It lets you put those equations. So let me put that equation really quick. So x1 is. Can somebody give me that? What was that matrix? Actually, I have it here. Don't worry about it. x2 prime is. This is that second matrix that we talked about. x1 and x3 is. What is x3? x1 plus x2 plus x3. Thank you. And some initial conditions, I don't know. Well, let's just pick some. 2, 3, 4. Okay. I'm missing something here. Error. Oh, come on. Okay. Well, I'll let you go, but try this, and I don't know, it didn't give me an error. This is on that remote RATS machine. Maybe we have to comment something, I don't know yet, but try this on your machine. And instead of looking at the time plot, which you will see something like this, right? But it's not that it's not a revelation if you see the time plot, because you don't, right? I mean, there's a system, a couple systems. Do the 3D plot, okay? 3D plot would be the sort of the equivalent of the phase portrait, but it's not the phase portrait. It's just for one initial condition. And so the bottom line is, since you know the Jordan canonical form, what do you know the solution to look like? And we should have seen it here. But if A is what do we say? 1, 1, 1, 0, negative 1. So how is the solutions going to behave in the space? You know, after some change of coordinates. Okay, so forget about the change of coordinates. Just take the canonical form. What's the system going to be looking like? Well, take a look. In the plane, in the x1, x2 plane, it's just that we've dealt with that, right? It was like that thing, only one probably like this, and probably like, I'm just guessing, right? Going away. So it means if you are in that plane, then that's how the solutions are, right? But what if you are outside of the plane? Well, the other direction, the eigenvector here is a vertical direction, and that's coming in, right? So can you imagine what would happen with a, you can't really imagine, with a point that's somewhere not on the axis but not in the plane? You would try to approach the xy plane, right? But in the same time, moving out, not spiraling, but moving out, right? So that's what you should see in that picture, okay? And you can rotate it, and it's pretty nice, okay? That's the goal of, and of course, imagine this, and then apply a t and a t inverse, which will skew the whole picture, right? But it won't change the essence. You'll give you a conjugate system. It will give you the same features, right? It's just like, I don't know, stretch in some direction and compress in another direction. Okay? That's the goal. So we'll talk about this on Wednesday. But I think you can already do a bunch of the homework that I assigned.